What is happening here?
What's happening?
Yeah. It has supports.
It's wobbling.
Wobbling, yeah.
Yeah.
What do you think the problem can be? Think about this.
Hallucinations.
Sorry?
Hallucinations?
Hallucinations? No, this is in real life. It's happening, but we need to try to understand why it is happening, right? So this is why we are here. Okay. Hi, welcome everyone to our second lecture. I believe we left it here last time, right? But we didn't have enough time to discuss, right, what is happening, because like me, you were also rushing to leave the room as soon as you can, right? Which I cannot blame you. Right. I just want you to think now, what could be the reason? It is just 1940s or 50s, I think. Engineering or engineers were quite well equipped at the time, but yet they couldn't predict this. I thought you were doing to your friends, sorry. Just a second. Okay, collapse. Okay, thanks everyone. So now please pay attention to our friend who knows the reason behind. Can you please tell your name first and explain what you think? Thank you.
I'm sorry if I messed this up, but this can all be summarized in one word: resonance.
Thank you. What do you think? Is he right or is he right? Resonance, thank you very much. And the thing is, again, my question, guys, this is quite an important point to make. Yes, it was resonance, what happened here, and the bridge collapsed. But the main question, or another question actually, guys, okay, once we start, and please try to make it on time, okay? So I really appreciate you coming to the lecture, but still it is a bit like, if we can try to make it a bit more on time, it will be much better without disruption. But to be honest, I really want to thank you again for joining, and because without students, we don't like lectures, we don't enjoy.
Yes, sir.
Correct. So please come, but try to be more on time, otherwise you will be a victim. Okay, so we were talking about resonance. What the resonance is, what do you think? What is the resonance? Right, we are just talking about resonance. So why the Tacoma Bridge collapsed? Didn't engineers at the time know about resonance? Maybe yes, maybe not. This is the problem, guys, so please think about that. And later on, we will be also talking about Millennium Bridge. Who knows where the Millennium Bridge is? Millennium Bridge, yes. So in London, right? Is it? Yeah. Okay. So it is in London, and it was opened because, as the name implies, it was Millennium Bridge, so it was opened early 2000 probably, or 2000 maybe. And a similar problem actually we had in also Millennium Bridge. Shortly after it was opening, they had to shut it down, close it for pedestrians, because again, it was extra, or unacceptable wobbling and vibration levels we observed. So we should expect engineers to do a bit better after this kind of disasters, but something happening. And still, we sometimes are not able to design things as we're supposed to be. So this is why we are taking design unit, right? Or dynamics, vibrations. We are trying to give you the main idea behind what is happening and how they could be prevented. Let's hear. So, which will make you later on possibly a lot of money. Why? How? After Millennium Bridge opened, again, when it started wobbling, they didn't know what to do and they were looking for some solutions, and they went for, or maybe the other company actually, came to them and they told, okay, we can provide the solution, but you need to pay us millions. The solution was very simple though, but they knew the answer anyway. Which company it was? You will make your search later on, and you will find a kind of consultancy company or an engineering design company, big one. They offer them a solution, very simple one, just add couple dampers in some strategic locations. But how did they know where to put this? Yes, they were not my students, but still, they studied engineering and they know the answer, which brought them a lot of fame, fixing relatively new bridge with very simple solution, elegant solution, and millions of pounds. So, you see, what we are talking about today means job, means experience, means income or potential income for many of us guys. So, this is why we are investigating. But in order to solve complex problems in engineering, we first start with really little by little from the first principles. So this is how we analyze engineering structures and make solutions and make life easier for people. And actually, what you are learning here has a direct influence on the quality or the life quality of people. So what you are doing is directly related to society. People benefit from your designs and analysis. But this is how it starts. This is what people don't see when you provide them answers or engineering solutions in general. So, it doesn't matter how complex the structure is. It doesn't matter if it is a plane or, I don't know, any other automobile, whatever it is, or I don't know, even buildings. By the way, the same company sold the solution for this Millennium Bridge, was also consulting for the MACD for reducing vibrations. Why do you think we could have vibrations in MACD here, apart from earthquakes?
The machines in the workshop.
Perfect. Perfect. I really hope now they are not working full time, but I really hope next year or whatever, during the semester, you will not feel someone working down there with tensile testing or fatigue testing machine and you feel it here. Because this is why they were paid and this is how they helped, they put input to the MACD project to make sure that vibration is not an issue in the building. For example, if one of your friends running down here, so the other friend up there shouldn't feel the vibrations, right? So there are really different issues, there are different examples that you can give, but these are the things. For example, when it is very windy outside, gusty or something, so you don't feel that inside as well. So, but the thing is, the beauty of the thing is that actually there are just three simple elements that you need to put into analysis to understand how you provide solutions to those complex problems. So these are quite clear here. Spring, damper, mass. We have three components. It doesn't change at all. Again, this is the beauty, guys. So three simple things, and you can solve the most complex problems using those three simple elements. Again, the mass is for storing some energy. The spring, another form of energy. One is potential, one is kinetic, right? And there is a damper in the system, which is an indispensable component because you are eliminating the unintended vibrations by these elements, shock absorbers, dampers. Again, as I said earlier, in Millennium Bridge, simple addition of couple dampers solve the problem and cost millions. So you may be the one diverting the millions to yourself if you know those three simple things and use them cleverly, right? Good. So in any vibration analysis, we have 4 simple steps. And it is actually common for many different engineering problems in physics as well. I don't know, in maybe chemistry as well, but it may not be that relevant here. So we are talking mostly about physics, because dynamics is a part of physics, right? So basically we are studying physics at different level or different branch. First, mathematical modeling. If we cannot create or extract the mathematical model, we cannot really take any step further. But once you obtain this mathematical model, you solved maybe 80% of the problem. Because the rest is just simple calculations, and the rest may be actually computers, MATLAB, whatever, even Excel can do a lot for you. But Excel or any other problem, software packages are not yet well developed to give you the correct mathematical modeling. I believe in a couple of years probably will bring maybe differences in this, AI and everything, right? So now it is getting a bit scary. But still, even AI will be able to get some point, some, I don't know, some approximation at least, and makes life easier for us. I believe in our lifetime and your lifetimes maybe, still engineers will need to provide some input in the decision process for making things, I don't know, possible. So this is the good thing. So once you create a mathematical model, you got 80% of the thing. The rest is just deriving the governing equations. What does governing equation mean? We have a system, and those governing equations means that the equations that can define the motion of this mathematical model. So imagine, I mean, again, this is a very beautiful thing. Imagine a car or a machine part is moving, vibrating, and with some simple equations, you can predict any motion of those, I don't know, mass, whatever it is. Still, with simple equations, if you can predict this, if you can really, not prediction, to be honest, you know exactly what it is. There is no prediction here. So you can really know which time, where it will be. It is very powerful and it gives you a lot of leverage. So you got the equations. Again, step 3, solving. You can do it yourself. Sometimes they are getting so complicated you may need to get assistance or help from, again, different softwares available there for you. So again, this is kind of a trivial step, but here we will try to know how, in the simplest terms, we engineers can provide these solutions. So this is why we are going with single degree of freedom systems only, where you will be able to get the solutions or answers easily. When it comes to 2-3 degree of freedom systems, it is getting more complicated, more complex, then we need to use computers. But here, you will not need, in this introduction kind of to vibration classes, you will not need computers to help you in those simple calculations. And then, step 3. This is again something, your input as an engineer is more important. Interpretation. It really depends on your own skills, your own experiences and everything. So this is again, I think, the most important thing which can benefit you and the society. Because until step 4, I am sure all designers working on Millennium Bridge were able to get solutions and they knew like, how the structure would behave according to them, but when they were interpreting the results, probably they did something, or they missed something, to be honest, maybe because of the lack of experience. So the maybe more critical approach, or the most critical sections are step 1 and step 4. In the middle, you will do it somehow, or anyone could do it. So, again, I tried to explain why we are creating these mathematical models, because without mathematical models, it is really hard to start approaching the problem. So once you have the mathematical model, you know how you can approach it. So this is the first step that we need to. Sorry, is it? Am I disturbing your ears, hurting your ears? I will try to. Okay. So, different people can come up with different mathematical models of the same problem. It really depends what we want to get from the mathematical model and from the solution. Again, this really depends on the experience of the engineer or analysis, but by the time when you get more involved with solution of the problems, I believe you will be at a better position to make some conclusions and interpret the results. So what I mean by different mathematical models here, a forging hammer, or it could be any other, I don't know, testing equipment that we have downstairs. So what kind of testing equipments we use as mechanical or aerospace engineers? Tensile testing, like, have you seen any testing machine? You didn't see any labs yet. Are you the so-called pandemic generation? So you've never been into any lab? Good. So it could be like some buckling or torsion or whatever. There are different types of mechanical tests that we can perform. This is something else, like it is kind of, again, a forging hammer, they call it. And the question, imagine you are working for a company producing those forging hammers, okay? And they tell you, okay, we need someone to make kind of vibration analysis for our forging hammers. I would ask why. It's just a forging hammer. What kind of, why anyone would need to perform any vibration analysis, right? I think I probably provided the answer earlier. For example, if this hammer is working downstairs in the basement, obviously we don't want anyone else to get the vibrations from this forging machine, right? So this can be one reason. What else could be? For example, probably they are using some elastic pads here, okay? So why? Why we use elastic pads there? Right. So we had 3 different elements, right? Mass, spring, damper. So this elastic pads working as shock absorbers or dampers, right? Correct. So depending on the mass and depending on different parameters, maybe your job can be to design or select the elastic pad material. So from which material? Of course, like, there are different types of, I cannot remember now. Okay, plastics. But again, you need to select one. So you may need to perform vibration analysis for selecting one. Or there is a foundation block. Maybe you are manufacturing or someone manufacturing this foundation block, and you need to provide some specification when you buy it. Okay? So University of Manchester wants to buy one of these machines, and they want to put it to basement. And as the manufacturer of the hammer, you need to tell Manchester that, okay, if you want to buy this machine in technical specifications, you need to tell them what type of foundation block they need, or you need to provide them the foundation block as well, and you need to manufacture this also, right? So for different reasons, you may need to make different vibration analysis. And depending on your purpose, you can create different mathematical models. One can be more simpler in a way if you are just, for example, if you are just interested on the foundation block, you can maybe make a more simpler and to the purpose actually, simple, but simple doesn't mean that less accurate all the time. So again, this may be better for your purpose. If you are talking about this elastic material here, then you may want to provide a different mathematical model. So it really depends what you want from the analysis. This is very important. And imagine now, you have the lecture material, so you can see actually that we can create quite different mathematical models. Again, the main point here, it depends. It depends what you want. If you are interested about the rider and rider's comfort only, then maybe, where it is, maybe the first one, maybe this one could provide you enough solution. Do you think so? It may not, to be honest. If you are really interested about rider, maybe you may want to go a bit more like complex mechanism, which is kind of giving you more information about the rider. So by now, probably like, at least you use maybe motorbike or bicycle, right? So, or in a car. If you are in a car, for example, or on a motorbike, we will talk later, but there will be some type of different characteristics of vibration. For example, what could be the potential danger to the rider if the motorbike is producing some specific type of vibrations? I mean, you can be uncomfortable, for sure, right? But what else you think?
Falling off the bike?
Can be, definitely. You can lose control, definitely.
I think you forgot to mention something about the potential health impacts on the rider, as in certain impacts. If they're too strong, they could perhaps might have an effect on the spine or the back.
Exactly. This may also be the case as well. Correct. So I was thinking about different health and safety issues, but yeah, this is also a possibility. So it may even create some hard dynamic impacts as well, which which our body parts may not be able to resist to. Okay, I would give another example, but I need to move a bit forward. But just, I want you to think, guys, do you know kidney stones? Have you heard about kidney stones? You heard. Do you know kidney stones? It depends on the individual anyway, but sometimes some small stones or particles, crystals, can be accumulated in your kidneys, which has a very sharp pain. I slightly had an issue with that before. God forbid, so it is really painful. I hope you will not get anything like that. The question: how vibration and kidney stones could be related? Think about this. We will come later in in a couple of weeks. I will tell you a bit more details about that.
I've got myself a good guess.
Sorry?
I've got myself a guess.
Maybe. So, again, it is about sending some ultrasounds to your body, and you are trying to match, you are trying to actually create a resonance in the kidney stones. But again, I think I will leave it here, but you can also make some search about this. Thank you. Now we know that depending on our purposes, we can create different mathematical models. So now let's try to create now we are okay with the mathematical models, but we need to also obtain the second step. What was it? Obtaining the governing equations. So how we will do that? Now we know that when we are talking about vibrations, we are talking about something in motion. So when a rigid body is in motion, which equation we can use? Newton, first one, second one, third one. There are three things, guys, Newton's laws. I mean, all our lectures in mechanics and in dynamics, we are basing almost all our arguments on Newton's three laws. What was the first one? Right. The second one? Correct. Third one? Correct. So which one do you think we can use here? Second one. Why? F, MA. How we call it? Apart from second one? Newton's law of? Great. So this is why we can use it to get a solution, get the governing equation for a simple mass. So you can see we have spring and mass. Initially, we just get rid of the damper because it is complicating things a bit. So we want to start with the simplest version. So we got rid of this damper for now, and we have spring and the mass. Here shows us the equilibrium position where the mass is in equilibrium and it is not moving at all. So here you can see we applied x to the mass, a displacement towards right. What do you expect? If we would leave it, what would happen? Do you think the mass would go to equilibrium position 0 and stop there, or it would go a bit further, come back? It's all right, yeah.
It depends.
On.
If you have enough damping, if it goes, it will be, if your first case was that it goes, and then it goes back to the equilibrium position and completely stops. This is what, I think this is called critical damping. Am I right?
Critical damping, we need to have some dampers for it. Otherwise, yeah.
Wait, but could friction act as a damper?
We don't have damper here. Sorry?
Friction could act as a damper, right?
It could have an effect as a damper, kind of, but for a certain level. So I don't think it would be as effective as a damper, but definitely it would have an effect on the level of the motion. So thinking here, I think we need to write it somewhere. So if the supporting surface is smooth, so if there is no friction, as your friend highlighted, then you would expect it to go the other side of the equilibrium position and oscillate back and forth, provided that no friction exists. So if there will be a friction, obviously it will depend on the friction coefficient as well. So in order to apply, or in order to get an equation of motion, we are applying Newton's second law, where it is, when the mass is displaced to the right by amount of x. So how we can write it? So let's see. Just remember, in our first lecture, I told that something that we need to remember is the free body diagrams. Here you can see the free body diagram, and you can see why we need that. So in order to provide the correct equations, first we need to construct the correct free body diagrams. So what does it mean? We are isolating the mass from the system. After isolating, you have to include all forces on the mass as it was in the system before. So once we isolated, cut the spring from here, we know that spring trying to pull because the mass is displaced towards right now, right? It is on the right side of the equilibrium position and the spring is pulling it back. So this is why we have F. We call it restoring force. And it is Kx. This is, you know, from I think high school. Spring force Kx, right? Displacement times the elasticity of the spring. We also have the weight, mg, of the mass. And we have Nb. What is Nb? Reaction, great. So it is a reaction force. Now, I believe we have all forces applied on the body. As we said, this Kx is restoring force, trying to pull the body, pull the mass to the equilibrium position back. And in mechanics, I think it was used like this because it's a convention that we are using in dynamics, and I believe it was also used the same way in mechanics as well. If you don't know the sense of a force or a displacement in mechanics, assume that the right is positive, and if you don't know the sense of any quantity, assume that it is acting towards right. Assume that and take it as a positive quantity. So if you do it consistently and if you perform your calculations at the end, if the result will be negative, it means that you took it in the wrong direction. You can simply change the direction, but you have to be consistent with what you are doing. So this is why later on I am giving you a couple slides as well, the things that you need to remember and apply consistently for all calculations. So please try to stick with this routine and take all unknown quantities positive in all your calculations, if it is unknown. So we don't know where the sense of acceleration at this point, so we are assuming that the acceleration is acting towards right. Sorry. Last year, I don't know, maybe it was because of this corona stuff or whatever, when I was teaching, almost in every lecture, I was losing my kind of voice in a different and weird way, and it was causing a lot of students were mocking. This year, I think it is about to start as well, so I hope it will not happen that much. So, we assume it is positive towards right, and here it is our beautiful and powerful equation, FMA. Simple, but so powerful. And we are again going to use it quite often. So, what does it mean left hand side? The total, the sum of all forces acting on a body equal mass times acceleration. So, on the left hand side, we have, again, you can see that we are assuming positive towards right, and you can see our Kx acting in negative direction, so this is why minus Kx, and we assume that acceleration is positive, this is why it is mx double dot. So if I have acceleration, you can see we can show it by x double dot. X is displacement. X one dot means, if we have only one dot on top of x, it means velocity, the first time derivative. If you have two dots on top, acceleration, 2 times you are taking derivative, time derivative. Right. So this has been observed in different mechanisms, different structures. So we know this as a simple harmonic motion because the displacement x and acceleration are proportional. So if they are proportional, negatively proportional actually, if they are proportional in a way, we call the resulting motion or the motion itself as a simple harmonic motion, and I'm sure you observed it in different parts. Simple harmonic motion, normally we see it in pendulums, right? Or springs in vertical direction, but the same applies when a mass actually moving along the horizontal line. So this is, I think, quite important thing that we need to know and relate. Okay, so we are just now rearranging the terms and we are getting our, again, elegant, very beautiful equation. We call it like standard form, but it is a homogeneous second order differential equation. And I'm sure, you recognize that actually this omega n is here the natural frequency, omega and k over m. It's quite simple things, but it is worth again mentioning. We can obtain the similar equations by a system in vertical direction. The only thing you need to do is just provide this free body diagram, and you will see actually the weight is cancelling in this equation, and you are getting almost again, not almost, you are getting the same equation again, but just instead of x here you have y, because you are using this time the coordinate y when you obtain the equation. That's all. That's it. Sometimes my students last couple of years, previously, they told me that it was a bit confusing for them and they really didn't get how it could be this way, and I provided them some extra free body diagrams from other textbook. So I hope this will be a bit more clarifying at this point. So it is really important to realize before you attempt the solution of any problem, try to understand the initial conditions, how it starts, where it starts to the motion. Very important. So if we see that actually the mass is moving in positive x direction, it could be y as well, no matter, it doesn't matter. If we are measuring the x from the equilibrium position, it is very important to recognize that. Then we can ignore the weight because it is kind of cancelling each other anyway. But again, you need to make sure that the body is starting its motion from the equilibrium position. Okay? So equilibrium position means we have the m here, and because of the weight, when you leave it, it will go to another equilibrium position to balance the weight. Right? So the weight actually balanced by the forces developed in the spring in a way. So it is really important to understand this reality. So at the end, you are getting the same equations anyway. Right. So as I said, this is a homogeneous differential equation. What does it mean, homogeneous? Right, so if the right hand side of the equation is 0, simply it means also the equation is homogeneous differential equation. And I believe based on I don't know, different mathematics probably lectures you took already, some differential equations, some I don't know how they call it, advanced engineering mathematics. So you know already that actually the solution of this standard form can be given with this equation. Quite simple, there are different forms of the solution anyway, so it doesn't really matter again which form of the solution you are using. It really depends on the initial boundary conditions of the problem, as you will see later on when we attempt to solve some problems. The point here I want to make is, I think it is the first time that you see in our lecture slides that actually we have a purple background in some equations. When you see the purple, it means great news for you. Why? Because if you see any equation in my lecture notes with a purple background, it means that these equations will be available to you in the exam. In the exam, it will be kind of an attachment, appendix to your exam paper. So you don't need to remember those equations at all, because our aim is not in dynamics unit. We are not, or I'm not aiming you to derive some equations or use them. I mean, again, it may be useful sometimes, but again, this is not a math lecture. Here, the point is how you will use the mathematical knowledge and information to provide some solutions to engineering problems, right? So, if you see this background, it means that you will get these equations. A and B, you know them, they are constants of equation, so we can find them, or integration. So we can find them depending on how you find the integration constants in a differential equation. By boundary conditions. So this is why it is really important to understand at the beginning, like, you know, where the motion starts, how it starts, where it starts, what are the initial conditions. If they say an initial velocity of 10 meters per second, again, this gives an idea to us to find out what are those A and B's, the coefficients. If they say it starts from the motion from x equal to 5 meters, again, this is an initial condition, and it will help us to identify what are those A and B. If you find the A and B's, we will be able to find the x. What was the x? Displacement. So, if you know the A and B from the initial boundary conditions, it means that you can calculate the displacement, the position of the mass at any point as a function of time. If they ask you, like, 5 seconds later where it will be, you will say second. Put them in, and it is there. This is why you are calling you, why they will be calling you engineers, right? It's kind of fortune telling with data. Right. So this is displacement. How you get the velocity? Right. First time derivative, right? Taking one time, derive it, time derivative. So yeah, first time derivative of this x gives you velocity. If you derive it one more time, then you get acceleration. Again, it is not the x only, it is not the displacement only that you can tell, but you can say them, okay, I have really, I am educated with high engineering calculations and everything, and if you pay me more, I can even tell you the velocity and acceleration of the mass as well. So, you know, how powerful you are. Now, let's try to see how we use those initial boundary conditions. Imagine now they are giving us some initial conditions. They say the mass actually displaced as much as x1. So this is the mass. I am the mass. I have a mass, increasing unfortunately constantly. So this is my equilibrium position. And I displaced to x1 to the right, and also the mass is given as an initial velocity v1. So these are really great things for us, because normally in a problem probably they will give you, or I will give you, someone will give you, what is the x1? They will say x1 is 1 meter, for example, to the right. v1 is 5 meters per second, for example. Then this will give you an opportunity to find out what are those A and B's in this displacement equation. How you will do that? You only need to substitute the values given to you in the main x displacement equation. So if you put x1 for x, and then the time is 0, because we are talking about initial boundary conditions. Initial boundary condition means the conditions at t equal to 0, right? So at t0 we have x equal to x1, and the solution will give us, actually when you will just substitute them, you will get b equal x1. And if you do the same, happening, if you do the same for velocity when the time is 0, then you find what a is. So it means, you see, how simple is that? You already got what are A and B, the constants in the equation. So it means that you already have the full equation, which gives you, again, powerful tool to determine the location of the mass anytime. And the equation X becomes like this, because this is A, right? This is A, and this is B. We already found that. Okay. So, yeah.
In the previous situation, can we use the work energy method to get because the force is conservative, and in that situation, how would we account for the kinetic energy of the...
You see how clever he is. Thank you, well done. This is a really important thing, and it is a really good way to come up with some comments. There are different, we are just using now the mechanics model, Newton's equations, but also you can use different energy methods. It is a really great thing. However, since I am providing an introduction only here, you will not be responsible for energy methods. The methods, energy methods, they are also available in our textbooks, main textbook, but I just, due to again our time limitations and my limits for 4 weeks for vibrations only, I have to exclude them. But it is possible. Thank you. This is a very good point. But you see, I forgot what I was telling about. Yeah. I forgot what I was telling. I really planned to tell something. Okay, it is back. It is back. It is back now. So far, I am sure it is quite simple. I mean, you may have some slight questions at some points, but I believe that they are quite straightforward anyway. But the main thing confusing you guys, when I'm telling the story, it is, well, yeah, this is that, it is quite simple, blah, blah. But when you attempt yourself to solve a question, things getting a bit like, challenging. And one of the biggest challenges of my students so far that I observed, when they see different forms of equations, they are getting confused. Which one I'm going to use? In some parts, you can see, actually, with some simple manipulations of the equation, you can see that we can just simplify the equation as like this one. And you will get also this equation as well. You can see it is with purple background as well. Which one you need to use? In some formulations, when you will check, if you check some textbook, different textbooks, for example, instead of x, a sine, it will give you an equation, a cos, b sine, for example. Again, this is the point where the confusion comes. Don't get confused. They are all the same. Okay? This is the point. But sometimes, depending on the question, what is given to you, this is why I'm telling you it is very important to understand what is given to you first. Analyze what is given before you start solution. It will save you time. In some specific problem, for example, later on we will talk about this, but this is called phase angle. If phase angle is given to you specifically, then obviously you cannot use this equation. You can use, but you need a lot of different manipulations again to exclude the phi, the phase angle. So, depends on the initial boundary conditions and what is given to you, you need to pick the right one. How you will do that? You need to solve as many questions as you can to get more experience, and you will feel more confident when you are attempting to solve different questions. So here again, another video, but it's a very simple one. Sometimes my students were asking me, okay, you are talking about one mass going back and forth, and then you are giving us a graph, sine graph, and how they are related, how mass is like in a work kind of moving in horizontal plane, how it is related to a sine motion. It is very simplistic, it is for high school things, but again, still it is kind of demonstrating how actually the motions are related with sine or cosine waves. So here you can see, depending on where the mass starting its motion, your graph can be a cosine graph or sine graph, which is also highlighting that initial boundary conditions actually telling you which equation to use. I don't want to take much of your time, guys. Thank you very much for joining. Next time we will continue from here. Thanks a lot.
I need to catch a train, but I put a question on the discussion board.
Right.
Just at the end of that slideshow with an example.
I saw it.
Yeah.
I didn't have time
Yeah,
to
that's
respond,
okay, yeah.
but I'm going to upload the solution,
Yeah.
so you will be able to compare your result
Yeah,
with.
right, thanks
And
a lot.
you are the first one to post anything. Thank you very much for that.
worries.
Okay.
Is it?
Keep
Did I use
posting.
the wrong equation? Or
Sorry.
did I use the right equation, or was it?
I really didn't have time
Yeah.
to
no
check,
worries.
but yeah.
Right. Thank you.
Thanks.
Selim
Merhaba.
ben, merhaba, nasılsınız?
Merhabalar, memnun oldum. Sağ ol, iyiyim. Sen
Memnun
nasılsın?
oldum Ben de. Ben ilk dersinize gelememiştim de ilk defa geldim derste.
Hoş geldin o zaman.
Pazartesi gelememiştim.
Selim demiştin.
Selim, evet.
Selim.
Geçen sene
Soy isim?
arkadaşlarım- Ha?
Soy isim?
Eryiğit.
Tamam. Bir dakika vaktim var. Şunları toparlayayım. Hoca derse başlayacak. Hayır.
It is even like wrong. Students are getting really tired. I'm tired. Probably you are. Very tired. Sorry about that. Okay, I think. Good luck. See you later. See you.
Sorry, someone had dropped this.
This is a good place to put it.
Yeah, I'll be aware, thanks. Ja,